Chapter 4, Applications of Derivatives. Section 4.1, Extreme Values of Functions. What we're going to do is we'll be able to find out, or we'll be able to know how to locate and identify extreme values, that means maximum and minimum values of a function, from the derivative of the function. How to find the optimal way of solving a problem, and of course how to find the minimum and maximum values of a function. Definition: let f be a function with domain D. Then f has an absolute maximum value on D at a point C if all the other f of x's would be less than or equal to f of c for all the x's in the domain D. And f has an absolute minimum value on D at x equal to c if all the f of x's or all the y values would be greater than or equal to f of c for all the x's in the domain D. Sometimes the maximum and minimum values are often referred to as extreme values. So when we're talking about extreme values of a function, it's either the maximum or the minimum values. Okay, for example, on a closed interval from minus pi over 2 to pi over 2, we are to find the absolute minimum and the absolute maximum of the function y is equal to sine of x. Now, y equal to sine of x would be the blue curve that goes from -1 to 1. So obviously, from the graph, we can see now that at x equal to minus pi over 2, the sine of minus pi over 2 is -1. And that is the absolute minimum of the function y equal to sine x on the interval from minus pi over 2 to pi over 2. Now, at x equal to pi over 2, then we know that the sine of pi over 2 is equal to 1, and so that is our absolute maximum. And here, that's where the minimum occurs. That's where the absolute maximum occurs when x is equal to pi over 2. Okay, now for the function, for the cosine function, which is the red curve, we can see that the absolute minimum occurs at the two endpoints. So at x equal to minus pi over 2, as well as pi over 2, the cosine of minus pi over 2 and it's equal to 0. At the same time, the cosine of pi over 2 is equal to 0. And so the absolute minimum occurs in 2 points. Okay. Now what about the maximum value of the cosine function? Well, the maximum occurs when the cosine, or rather when the angle of cosine is 0, because cosine of 0 is equal to 1. So at x equal to 0, cosine of 0 is 1, so that becomes the absolute maximum of y equal to cosine of x on the interval from minus pi over 2 to pi over 2. And these values can depend on the domain that we've chosen for a given function. And we will look into this later when we work on some more examples and exercises at the end of the section. Okay, this is based on page 185 of your textbook, where they took the function y equal to x squared and then looked at different domains and find out whether in a particular domain, whether there is an absolute maximum or an absolute minimum. Now let's look at letter A. In letter A, we have that y is equal to x squared in the whole real line. And if we look at this graph, Notice that it does have an absolute minimum occurring at x equal to 0, but it has no absolute maximum because this graph will continue on to plus infinity as well as on the other side of the right side of the x-axis. So sure enough, if we are looking at the domain uh, on the entire number line, then y equal to x squared has no absolute maximum. Okay, letter B. Now in letter B, we can find the domain to be from 0 to 2. And from 0 to 2, it occurs at x equal to 0 as the absolute minimum. And when x is equal to 2, then y attains its absolute maximum at the value y equal to x squared, which is at 4. Because when x is 2, of course, y will be 4. Okay, now how about in letter C? In letter C, we have a half-open interval. It's open on the left side and closed on the right side, the other end of the interval. And here, we will not have an absolute minimum of the function because of the way that the domain was defined. So if it is on an open interval on the left side, then there is no absolute minimum. But on the right side, it occurs when x is equal to 2, then the absolute maximum is, or the absolute maximum value is 4. Okay, what about in letter D? In letter D, we have an open interval for the specified domain, and this will not have a maximum or a minimum, an absolute maximum or an absolute minimum. Okay, let's go now to Theorem 1, the extreme value theorem. Suppose that f is continuous on a closed interval, AB, then f attains both an absolute maximum value m, capital M, and an absolute minimum value small m in the closed interval AB. What does this mean? It means that you will find an x sub 1 and an x sub 2 in the closed interval AB where f of x sub 1 is the minimum value and f of x sub 2 is the maximum value. And that would mean that, of course, all the y values will stay between the absolute minimum and the absolute maximum for all the other x's in the interval AB. Okay. For theorem 1 to hold, f must be continuous on a closed interval. If you look at the previous slide, here where we were able to obtain the absolute maximum and minimum was on the example letter B, because it was on a closed interval and our function is continuous. Y equal to x squared is a parabola, so it's a continuous function. And so based on theorem 1, it says that if f is continuous on a closed interval, then f attains its absolute extreme values. So again, the theorem 1 will hold if we have those conditions that f is continuous and the domain is a closed interval. Okay, here are just some situations where the extreme values would occur in letter A, or right here in this first graph on the upper left. The minimum and the maximum values occurred at interior points. Okay, there's your maximum and there's your minimum point. Now here on the right, upper right, we have the maximum and the minimum points occurring at the end points right there. Okay, And it's also possible that you can have the maximum occurring at an interior point and the minimum occurring at one of the end points. Whereas here you have a minimum occurring at an interior point, whereas the maximum point occurs at an end point. So these are just the different possibilities of where a maximum and a minimum value can be found on a continuous function given a closed interval AB.